All right. So hi everybody. My name is Sebastian. I'm going to be talking about some of the RAM types that I found. I'm going to go over some of the more current ones like SRAM, DRAM, and then going to go over some of the newer ones that I found like uh, RAM, MRAM, obviously. And then there's this sort of interesting one that I found. It's a combination of SRAM, but implementing NTJs to make it non-volatile. So first going over DRAM. So here on the right, you can see it's a picture of the overall working cell. It consists of a single MOSFET transistor and a capacitor. The information is saved in the capacitor as charge. It is volatile, so you need to refresh the circuit every time because the capacitor responds to the discharging charge. So if you want to conserve your bit, you need to refresh to charge the capacitor again. DRAM is relatively slow. The speeds are listed around 50 nanoseconds, which is considered slow. But the benefit is that they're really cheap, simple to manufacture, and the cell area is small, so you can pack a lot of them and achieve very high densities with them. So the usual numbers that I found for like a diameter is 40 nanometers. Some of the limitations for DRAM in terms of scalability is that it's not compatible with CMOS logic, which is something I found that was sort of desirable for implementing in to but I'm not really sure about that. And then it's been sort of hard to scale it below 10 nanometers. It's related to some issues with lithography. There's also some voltage scaling issues. So here in the transistor, I guess the voltage VB is not, or you can't really, or I guess as you go low in size, there's some leakage problems between the word line row and the actual capacitor when it's discharged. So yeah. Oh, and I guess I'll talk a little bit about how you actually write and read on the cell. So to write, you simply apply voltage in the bit line, and then you apply voltage in the word line. That's going to charge the capacitor. And to read, I believe it's also a combination of, well, it's like a different step process where you measure the voltage across the capacitor. And that will tell you if you have a 1 or a 0. So now we're moving on to SRAM. Here on the right, we have a typical cell consisting of 6 FET transistors. We have 2, the PG1, PG2, and then each of these NOT gates consist of another 2 transistors. So since the cell consists of 6 transistors instead of 1 for DRAM, we see that the area of the cell is usually much larger. The diameters are usually listed around 200 nanometers, but we get much faster speeds around 10 nanoseconds per cycle. Again, it is also volatile. And another advantage over DRAM is that it is CMOS compatible. Some limitations on scalability. Again, we have some lithography issues related to the roughness of the line edges when you want to make really small features. There's also some problems related with the materials where once you get to really small cell sizes, the dopant density is, I guess, even for highly doped materials, the density is small enough that when you get to really small cell sizes, you end up with maybe an average number of dopants per cell of like 27. I think I saw some numbers that sit around that. So that's going to create really big fluctuations per cell, and so that can change the performance of every individual cell across a single chip, which is not desirable. And also the voltages, the operating voltages for a single cell don't scale well with size. So a really big size change doesn't really mean like a smaller voltages, which is also a problem because you end up with leakage and a lot of stress on your materials. So now I'm going to talk about this example that I found of SRAM implementing some MTJs to store the information and make it non-volatile. This is desirable for power saving since you don't need to actively keep your device at a voltage. You can put it on a standby mode, which basically you take off the voltage of it, but you still save the information. Also in this specific paper, they implemented on CMOS logic, so it is CMOS compatible. They listed an area for the MTJ alone, which is you get like a diameter of 50 nanometers per each MTJ, but this is on top of the SRAM chip. So we also have the area of the actual SRAM chip. And the simulations that they listed, they listed some store and write times of 2 nanoseconds. The store and write times they mentioned is the time that it takes to write the information in the MTJs, and also for the MTJs to sort of write the information back in the SRAM. Also something novel that the paper claims is that they were able to switch the MTJs from the parallel or anti-parallel state using a spin Hall effect, where they actually drive a big current across a heavy metal base instead of actually sending a current through the MTJ. But they mentioned that in the out of plane configuration, where the magnetization of the layers is in the out of plane direction, it's relatively hard to do it if you don't have a big enough current. So they also introduced a SCT ride current going across the actual material to aid in the switching, which they claim that since the SCT current, sorry, is not as large as you needed to switch it if it was the SCT current by itself, it increases the endurance of the material. Okay, so another sort of upcoming memory type that it's popular is AirR RAM. So this is a non-volatile type of memory. It's also compatible with CMOS. It's mainly focused on high density storage because it's I think the cell sizes that I found are usually in the 10-15 nanometer scale, which is very small, even comparing it to DRAM. But it's still in the very early stages, I believe. So it has some issues, but well, I'll talk a bit about that in a little bit. So just as a really quick overview of how AirR RAM works it's similar to MRAM in that we have two states, a high resistive state and a low resistive state, but the switching is done by applying a voltage across a dielectric. So the way it works is you start with your non-conducting resistive layer in the high resistance state. And if you apply a really high voltage to it, you can sort of put it in this switching state where after that, you can, depending on the voltage that you apply between the layer, you can actually make it go between a high resistive state and a low resistive state. The main mechanisms of why this happens are still not very well understood, but basically the middle layer is usually composed of an oxide. So when you apply a voltage, you sort of have this diffusion of oxygen ions that leave some vacancies in the material, and those vacancies serve as like a channel for your electrons. So this leads me to talk about some of the issues. Because it uses this sort of like diffusion of ions, it's very sensitive to surface and junction imperfections. It also leads to poor uniformity on the actual device parameters. So they mentioned that RAM usually has very poor uniformity spatially, so between actual cells in a single chip and also over time. They also mentioned that there's some problems with oxygen accumulation between the interfaces of the resistive layer and the electrodes. And as I said, the conducting mechanism is still not fully understood. Oh, sorry. So I think they do not have like a sort of concise or like an agreed universally physical model for it, but they have some ideas for it, which is what I talk about.
10 more seconds, so maybe just wrap up.
Oh, okay, sorry. So this is some table with some values, and I'm going to skip it. And then, well, I was going to talk about MRAM. So here are some of the types. Here's STT-RAM and the three-domain model, which they call. So just real quick, some of the values that I found for STT-RAM, some of the ratios are very low. Again, you can achieve a high density. It is potential to go for sub 10 nanometer cell sizes. And yeah, there's still some problems because it's very early in the stages of production. But yeah, it has the potential to become the universal memory type. Okay, that's all I have.
Thank you. Any questions for Sebastian?
Yeah, I got a question, maybe to give you a little bit of an opportunity to go over the slide that you had to go a little quick. But I saw in the corner there, spin orbit, sorry, the next one, spin orbit torque. Is that like fundamentally better than spin transfer torque, or do they work together?
So
different.
I think, well, they're different they're different architectures. So they both have their trade-offs. I believe spin orbit torque has a larger cell size normally, but I think they have better endurance, like in terms of they usually don't get as damaged because they don't have so they have two different types of current. You have a read current, which actually goes through your material, which is sort of the current that damages your material. But the actual write current doesn't go through the material, so that usually improves your how much the material lasts. Where in STT-RAM, your read and write current both go through the material, and yeah, I think just having current through your material usually damages it over time.
Thank you.
I had a question too.
Go ahead, Nick.
In the RAM slide, I was just wondering, I mean, you said the physical origins might not be known, but it seems like the hysteresis sweeps almost like they look pretty different going forward and backwards. Is there kind of any explanation as to?
Yeah, I didn't talk about these loops. So I guess there are actually two different types of RAM materials. You have bipolar and unipolar. The unipolar is here on the left. This is the well, basically you can go to the high state and the low state independent of the polarity of the voltage they apply. Where in the unipolar one, you can only go to the high state on one polarity, and you can only go to the low state on the other polarity. So I'll just go over. I can go over this loop, for example. So
I think maybe we'll stop it there. Thank you so much, but just because we're out of time. Thank you. Yeah, but that's a good question, and it's good to go over these loops, make sure we understand them if you're interested in RAM. Thanks so much, Sebastian.